You run a query, select star from users where id equals 7. Your table has 100 million rows. The query comes back in under 1 millisecond. No loading spinner, no delay, just instant. How is that even possible? You did not scan 100 million rows. Your database did not even look at most of them. It used a data structure called a B-tree, and it found that record in roughly 3 comparisons. In this video, we are going to build up exactly how that works, from the problem all the way through real production databases. By the end, you will understand why your queries are fast when they are slow and what to do about it. Picture a table with 100 million users. You need to find one person by their ID. The naive approach is a full table scan. Start at row 1, read it, check the ID, move on. If the ID you want is near the end, you might read every single row before you find it. That is O of n time. At 100 million rows, even if each comparison takes 1 nanosecond, you are looking at 100 milliseconds per query. Scale that to thousands of concurrent users and your database falls over. Clearly, scanning every row is not a solution. We need a structure that lets us skip almost everything and jump straight to the answer. A B-tree is a self-balancing tree where each node holds multiple keys and multiple child pointers. The keys inside a node are always sorted. So if you are looking for a value and you land on a node, you can use binary search to find which child pointer to follow next. Every level of the tree eliminates a huge fraction of the remaining possibilities. The root node is at the top. Internal nodes sit in the middle, routing searches. Leaf nodes sit at the bottom and hold the actual data or pointers to it. The critical property is that all leaf nodes are at exactly the same depth. That is what makes the complexity predictable. Searching a B-tree is a top-down walk. Start at the root. Read the keys. If your target is less than the first key, follow the leftmost child pointer. If it falls between 2 keys, follow the pointer between them. If it is greater than all keys, follow the rightmost pointer. Keep walking down until you reach a leaf. At the leaf, scan the keys linearly. There are only a few of them, and either find your value or confirm it does not exist. For a tree of order 500 with 100 million records, the height is roughly log base 500 of 100 million, which works out to about 3 comparisons, 3 disk reads. Done. Every node in a B-tree has a maximum number of keys determined by the tree's order. Written as T, a node can hold at most 2 T-1 keys, and must hold at least T-1 keys once it has been filled and split. Keys within a node are always stored in sorted order. Between every pair of adjacent keys is a child pointer. So a node with 2 keys has 3 child pointers. This means a node with 1,000 keys has 1,001 children. That fan-out is why B-trees are so shallow. More keys per node means fewer levels, means fewer disk reads. When you insert a key into a full node, the node must split. Find the median key, push it up to the parent, and divide the remaining keys into 2 new child nodes. If the parent is also full, it splits too, and the promoted key propagates upward. In the rare case where the root itself is full, the root splits and the tree grows by exactly 1 level, creating a new root above it. This is the only way a B-tree ever increases in height. Splits always propagate upward, never sideways. This design keeps all leaves at the same depth, no matter how many inserts you do. The reason B-trees have high order, meaning many keys per node, is disk physics. A disk or SSD read operates on pages, typically 4 to 16 kilobytes at a time. You pay the same latency cost whether you read 1 byte or a full page. So the smart move is to pack as many keys as possible into each page. A binary search tree has at most 2 children per node, meaning height is log base 2 of n, which for 100 million records is about 27. 27 disk reads per query is slow. A B-tree with order 500 packs 500 keys into a single page. Height drops to 3 disk reads is fast. Real databases like PostgreSQL and MySQL do not use pure B-trees. They use a variant called B+ trees. Key difference is that internal nodes store only keys, no row data, which means you can pack even more keys into each internal node, making the tree shallower. All actual row data lives in the leaf nodes. And here's the clever part, leaf nodes are linked together in a doubly linked list. This means range queries, select star where age between 20 and 40, do not need to traverse the tree repeatedly. You do the O log n lookup to find the start of the range, then walk the leaf list linearly to collect results. When you run create index, your database builds a separate B+ tree on that column. The index tree stores the index column values as keys, sorted, and each leaf entry contains a pointer back to the corresponding row in the heap, the actual unsorted table. Now when your query has a where clause on that column, the planner can use the index to do a fast O log n lookup instead of a full scan. Without the index, every query on that column walks the entire heap. The index is essentially a pre-sorted copy of one column, maintained automatically by the database on every write. Indexes make reads fast, but they have real costs. Every insert, update, and delete must also update every index on that table. If you have 5 indexes, you are doing 6 writes per insert, 1 to the heap and 1 to each index. This write amplification slows down bulk loads and high write workloads. Indexes also consume disk space, sometimes doubling your table size, and as they grow, pages fragment and need vacuuming. The rule of thumb is to index columns that appear in where clauses, join conditions, or order by clauses on large tables. Do not index Boolean columns or columns with very few distinct values. The planner may ignore those indexes anyway. B-trees are everywhere. SQLite, PostgreSQL, MySQL, Oracle, SQL Server, MongoDB, and many others all rely on them as their primary index structure. You interact with B-trees every time you run a query with a where clause. Now you know why finding one row in 100 million takes 3 disk reads, why range queries are fast, why indexes cost writes, and when to add them versus when they hurt. The next time your query is slow, check if you are missing an index. And the next time it is fast, you know exactly which tree to thank. If this clicked, subscribe for more systems diagrams every week. There is a link in the description to the full B-tree visualization tool we use today. Drop a comment with the query that made you wonder about this stuff. Thanks for watching.